So we are spending about 50% of energy consumption just for us to sit here being comfortable, right? So nothing else, just be comfortable. And we're all part of this, right? And the reason is because this is such an important fundamental need for us to become so many comfort, right? So important that we often forget about the significant energy consumption. So first of all, this can only be worse. You can imagine that we just learned that we just broke the record of the hottest month in human history in this July, and things could be even worse in the years to come. So let's not forget the other side of the, not long ago, we also have one of the deadliest extreme weather event in Texas. So this all comes to reminds us the importance and the indispensable fact of how thermal comfort can be for us if there was no modern technology. And this is the reason why we cannot live without it. Right? So we need to spend so much energy just to maintain the temperature around us. Now, again, this is one of the plot you can see from a medical journal that if you have this temperature fluctuation, let me find my, right here, right? So, of course, you will have this temperature fluctuation and you have this physiological response to it. And if you don't do a good job in terms of providing a thermal environment to people, then some people, high-risk people, might get cardiovascular diseases, brain stroke, or even influenza, and so on and so forth. So essentially, this comes to this nexus, what I call a human energy building nexus, where we need thermal comfort, we need shelter, right? So that's why we have building. But in order to provide a thermal comfort, we fight against the gigantic thermal temperature difference between the indoor and outdoor. Right? Imagine this below freezing outdoor, but we'll feel very, very comfortable indoor. How large of the temperature of the energy we are spending to keep that gradient. So we have this human body fundamental need for thermal comfort, building do the heating and cooling HVAC to support this. And how much energy we are actually consuming, and can we do better than that? Can we improve the efficiency or completely using the renewable energy to achieve the same goal? To be a little more quantitative on this, here's what we, a very single plot that explains the concept, right? Here you see the sun is the only heat gain, right? If you consider the Earth, the sun, and the universe, there's nothing else, right? So the only sun that comes in, and you absorb some solar energy, and you emit, right? You emit based on the fundamental physics law. And the fact that we are sensing a higher global temperature is because the loss is slightly smaller year by year because of the increase in CO2. So that enhances the temperature, right? So imagine if you deal with a certain building on Earth, right? And that building can block all the sunlight, meanwhile emitting all the infrared. Then you can just cool down all the way to below ambient. And that's exactly what's happening in this blue curve. Right? So can we reversibly control the presence of metal back and forth? So essentially what we're doing is electroplating, right? So when you use electrochemical, you apply bias, you can deposit, here we're depositing copper on this top transparent electrode, then you form this copper thin film. And again, copper is very, very high reflectivity, very, very bad emitter. So this device overall will suppress the heat loss, make the building feels warmer. On the other hand, if you reverse bias, oxidize the copper, dissolve it back to the electrolyte, you are letting this electrolyte, which is water-based, exposed to the universe, and water is a very, very good thermal emitter. So here you are losing a lot of heat, basically close to black body radiation. Now here are a few advantages of this device. First of all, it's copper. It's made of water. If you want to imagine that you're going to cover this device to the building surface, it better be lower cost, it better be safe. And here's the reason why we pick those material combination. So you can see the emissivity will just keep there, even though the circuit is removed. On the other hand, the other system just go back, and this means it's very, very inefficient. It will self-discharge. And here's how we propose we can predict the performance. So a theory called affinity evidence theory, which is essentially taking the average of your material. You have water, you have copper, and you take the average of those. You get the average optical property. So we propose to use this as a tool, as a prediction tool, and also this is the basic optical equation that you can calculate the reflectance or the emittance of your material. So it turns out that the fitting was quite good, and it also told us some fundamental material deposition mechanism. So that's a very nice kind of engineering science when we not just push the performance, but also to provide a prediction tool. Coming back to the human side of this, right? How do we, instead of managing the whole building, can we manage human scale? Right? So we call wearable thermal regulation. So there's a lot of existing work, both from private sector and from university, about how do we do this. So I cannot explain everything, but just want to share a few recent work by our group with you. So we recently demonstrated this we call a variable emittance device. Right? We call it WEAF. Essentially, it's again using electrochemistry, but not using metal because it's much harder to make it wearable. So we kept that in our mind. But here we're using polymer, and we use this porous gold as the ion permeable infrared reflector and the electrolyte and everything. Now this is the active material, it's polyethylene, right? So essentially you can switch between a conducting state and insulating state, which will give you a different optical response. One optical trick we play is that because the material we're using is polymer, and polymer is much less conductive than metal, so you can't really use the same concept over there. So instead of using the polymer's intrinsic reflectivity like we did with copper, we add a back reflector to help us. All right, so you can also imagine to wear a battery on yourself is kind of unrealistic. So you also need to provide a few variable approaches. Now, this is one example that you can actually maintain the electrical conductivity, meanwhile give you the stretchability for out-of-plane conformal deformation. Just by cutting it, this is a kirigami cut. You can do the parallel cut. It's more suitable for your joint, and this is more suitable for like two-dimensional or more planar deformation like your torso and chest or back. Now, this is just one example, again using a thermal camera to demonstrate that even though the device is now bent, is cut, because the kirigami will maintain the in-plane conductivity, you can still operate the device. And you can see through the thermal camera. This is the heating mode, low emissivity heating mode, and this is the other mode. All right, so because again the benefit is now with electricity, electrically controllable. You can imagine you can couple with sensor, all kinds of wearable technology to create such a closed loop regulation. The simplest one is you put a thermometer with two coils, apply potential, and give you a state, and vice versa. Now, the nylon is also a very hygroscopic material. It has hydrogen bond. So when you sweat, your vapor will actually go between the nylon molecules, and that will expand. And when you expand only the bottom layer of it. So the top layer will still maintain the length, which will create this actuation. So it will bend up. And when you bend up, you can open up the pore, now enhance the sweat evaporation. Now the silver relative shield is also out of the way. You get two different mechanisms of cooling. Of course, when you this actually can go back and forth when your sweat dries out. All right, so with that, I just want to summarize that. I hope that showed you a few examples of how electrochemistry can play an important role in bringing better human and building thermoregulation. And we definitely want to see more and more multifunctionality devices and to perform cooling under all scenarios.